Stop. Let me share with you how the top 1% of automotive technicians use field trim to diagnose drivability concerns. Go ahead and grab your scan tools. Let's take a look. Make sure that you guys give us a like and a follow and turn on the little notification bell so this way you're alerted every time we drop a new video. On today's topic, we're going to be talking about field trim. This is not your standard field trim class. Trust me, you're not going to fall asleep. With this class here, we're going to learn a little bit about field trim, how it started, how it evolved, where we're at with it today. Plus, I'm also going to share with you two videos on two vehicles that I personally tested. So this way you can see how field trims change and adapt as the vehicle drives along down the road. If you're ready, let's go ahead and jump right in. Back in the old day, when it came to field trim, you were the field trim. So us as technicians back in the day with carburetors would have to use specialty tools like a flathead screwdriver or an actual carburetor adjustment tool to properly adjust the field trim or the adaptation of fuel consumption on a vehicle. So as the vehicle got older, wore down, the carburetor and fuel mixture components began to wear down, they would need to come into the shop where we would then take tools, just like a flathead screwdriver, to readjust the carburetor to get the vehicle back into its normal field trim. Now, if you guys have been around carburetors like I have, you were either using a propane enrichment rig, a vacuum gauge, or a 5-gas analyzer to adjust carburetors to make sure they were running tip-top. Unfortunately, because they were mechanical, they would break down quite often and also cause problems for the consumer, not only in the drivability format, but also out the tailpipe related to emissions. And this is why most manufacturers went to a feedback carburetor style as cars progressed and went down the road. Feedback carburetors. I can remember feedback carburetors as early as the 1980s. Obviously, I'm an 80s baby, but if you were around then, you would see carburetors such as this 4-barrel Quadrajet that's sitting right here on this image. These vehicles were equipped with a throttle position sensor, an MC, not a mic controller, but a mixture control solenoid, an oxygen sensor, and an engine computer that had a fuel management system built in. So now with the advent of engine computers, it was going to be looking at sensors such as throttle position and manifold absolute pressure, because we were using map sensors from speed density back in the day. And the computer would then make adjustments to the pulse width modulation of your mixture control solenoid. This was going to help achieve a better fuel control, giving us better output of emissions out of the tailpipe. And there's one sensor that I didn't mention, which was the oxygen sensor. The O2 sensor was also giving feedback back to the computer, letting it know what the content of oxygen in the exhaust was after internal combustion. And we're going to talk a little bit about that here in a bit. We also want to give thanks to GM for introducing and giving us Block Learn and Integrator. And I'm going to talk about what that is here in a bit. Load and speed. Thanks to GM and their 16-cell mapping, GM was the first manufacturer to give us as technicians this particular information. This was a 16-cell grid or map that the engine computer was using to then determine fuel control. Now, if you look at the y-axis, this would be your load, typically would be your map and your TPS sensor. And on the bottom, on your x-axis, this would be your engine speed based off of RPM. The engine computer was looking at this information to then make calculated decisions on how much fuel adjustment it needed to make, falling into one of these 16 cells. Now, GM was the first manufacturer that gave us this, and if you were using the old MT2500 or the brick, you would be able to see the load cell. Now, on a lot of newer vehicles, and I've seen this on Autel, it will give you the load cell number. Unfortunately, manufacturers aren't giving us the actual chart, so it's hard for us to determine if we're in the right load and speed cell. However, you can always take this with you. If you have a bad load sensor input, that's always going to affect your load and speed cell, which is going to equal either a bad drivability concern or bad emissions coming out of the tailpipe. To have good load and speed, we need to know what our priority sensors are. According to most manufacturers, some of the priority sensors would be engine load, which is going to be map, MAF, and TPS, engine speed, RPM, air fuel mixture done by the O2 sensor or the air fuel ratio sensor or a mixture of both, and ignition timing. This information is crucial for the PCM to make proper air-fuel adjustments to the vehicle to achieve proper performance and meet and exceed federal emission standards. What were to happen if a vehicle comes into your shop and one of your priority sensors is out of spec? For example, if a car comes in and you have a mass airflow that is underestimating the amount of air, isn't it true that that's going to cause a drivability concern and also set a check engine light for a possibility of an air-fuel mixture related code, such as a 171 or a 174? These types of situations are what we as drivability technicians always face when we're out on the field. This is why if we understand what a priority sensor is, that input is going to be super important to the PCM to help us make a better judgment call when it comes to continuing with our testing and evaluation of that particular vehicle. Who's zirconia? We might know it as a standard oxygen sensor, but the most common oxygen sensor used was a zirconia type O2 sensor. The oxygen sensor actually does not check for fuel in the exhaust. It actually checks for oxygen. So the oxygen sensor itself, just like the name entails, measures the concentration of oxygen left in the exhaust after internal combustion. This is why when some people say that if a vehicle has a misfire, the extra fuel is going to be sensed by the oxygen sensor and show a rich condition, which is false. If you've ever tested a zirconia O2 sensor by purposely causing a misfire because you're not compressing, igniting the air-fuel mixture, what's going to end up happening is you're going to have a bunch of oxygen going downstream. That oxygen content gets detected by the oxygen sensor in a lean fashion. So now the PCM is going to see an extra lean condition, not a rich condition. So always remember that the O2 sensor will be sensing oxygen content, not fuel. The typical zirconia O2 sensor has an operating range of 0 to 1 volt. Anything from 0 to 450 millivolts is going to be a lean condition, and anything above 450 millivolts to 1 volt is going to be a rich condition. So this way, it's easier for you to understand. If you see high voltage near 1 volt, it's running rich. If you see low voltage near 100 millivolts, it's running lean. A good way to understand an oxygen sensor operation is when voltage goes up, the PCM in turn will go lean. If the voltage on the oxygen sensor goes up, this is telling the computer the vehicle is running rich. What the PCM is going to do is then remove fuel, so this way it would lean it out. When the O2 sensor goes down, or the sine wave goes down, the PCM in turn is going to go rich. So if the PCM sees the voltage drop off, then the computer is going to enrich in the mixture to have the voltage come back up. The sine wave that you can see in this image here on the right-hand side is a result of the PCM continuously adjusting to keep the engine running efficient and within emission standards. This is why the PCM is continuously going from rich to lean, rich to lean. Most O2 sensors or zirconia O2 at about 2000 RPM should be between 1 to 3 hertz. If you guys remember what hertz is going to be one measurement within 1 second. So if we have 3 hertz, that means we would see 3 humps within 1 second of that O2 sensor switching. Propane enrichment test. Since I can remember going to school to become a smog technician, we were taught how to do a propane enrichment test. What I'm doing here is I have my oscilloscope plugged into my front and rear O2 sensor. What I did then is I added propane through an intake hose or a vacuum line, and you can see that my oxygen sensor went rich. I then removed the propane and notice how the oxygen sensor voltage begins to go lean. Now it stays lean because I induced a rich running condition. So now the computer is doing its thing and getting ready to start adapting. What I did then, once I went lean, is I did a snap throttle acceleration. If you guys are aware, whenever you go wide open throttle, the engine computer should go into open loop drive. So now when it does that, you're going to have maximum flow of fuel coming out of the injectors. So what we see here is I went full wide open throttle and the O2 sensor went rich. What I did then is I took my cursors and I'm going to start at the lowest point to the highest point and measure the time. A standard zirconia O2 needs to be within 50 to 100 milliseconds from lean to rich. Notice how this one was 284.9 milliseconds. This vehicle was suffering from not setting a catalytic converter monitor and an oxygen sensor monitor. Now, if you can see, this oxygen sensor is 184.9 milliseconds too slow. The engine computer in no way is going to allow to set the monitor if this O2 is that slow. We recommended replacing the oxygen sensor. Once we replaced it, we reran the test, which I hit my head every day because I didn't get a good capture. However, the vehicle was driven, monitors were set, and vehicle was inspected. So this is why it's always a good idea to run this particular test. So this way you can see how the O2 sensor is actually working. Now, I've always been asked, can you do this with the scan tool? My answer is, I've never tried it. If you guys want to go ahead and try it, and if it works, drop it in the comments. Let me know if it actually worked out. I haven't had a chance to do so, but if you guys can help me out, I would really, really appreciate it. Not all cars have just a zirconia O2. Some manufacturers have gone to an air-fuel ratio sensor or a wideband O2. This is basically two oxygen sensors pressed into one. When we're looking at an air-fuel ratio sensor, we're going to have a pump cell, and we're also going to have a nursed cell. Here, if we're looking at it, most of the time, engine computers are going to give you a small current measurement for these sensors, or some of them are going to give you a lambda reading. I prefer to look at the lambda reading. It's much more easy to understand. If, for example, you have a lean condition, you're going to see positive current being sent to the pump and pumping out oxygen from this particular cell. If you have a rich running condition, you're going to have the cell pumping oxygen into the actual zirconia cell here, and you're going to have a negative current. Now, if you guys understand lambda, if lambda goes above 1, then that means it's running lean, similar to what our current does. And if lambda goes below 1, that means it's running rich, just like what our current is going to do with our air-fuel ratio sensor. What I have here, thanks to Nissan, Toyota, I have some information for you guys that's really important when it comes to air-fuel ratio sensors. On Nissan, in order for us to have stoichiometric, or 14.7 parts of air to 1 part of fuel, that would be the equivalent of 1500 millivolts. 1500 millivolts is 1.5 volts. If on a Nissan you see 1.5 volts on an air-fuel ratio sensor, that is letting you know that the vehicle is in optimal air-fuel control. On Toyota, according to their service information, the air-fuel ratio can range from 3 volts to 3.6 volts. Optimal would be 3.3, which is equivalent to stoichiometric, perfect air-fuel ratio. So if you're working on a Toyota with an air-fuel ratio sensor, you'd want to see 3.3 volts, indicating that that air-fuel ratio sensor is spot on. I'd like to add here that vehicle manufacturers such as Toyota not only uses the front air-fuel ratio sensor, they're also using the rear O2. If you have a Toyota that comes into the shop, that rear O2 is going to be fine-tuning that air-fuel adjustment. If that rear O2 is out of whack, too slow, or contaminated, or has an exhaust leak anywhere, that might be throwing off your air-fuel ratio. So don't always assume that the air-fuel ratio sensor is the issue. If you have a 171, 172, 174, 175, you want to run proper tests to then determine which one of those bad boys is the one causing your problem. Back in the old feedback carburetor days, as I was mentioning before, GM introduced the integrator, which was our short-term fuel trim. This was given to us in binary, which was 0 to 255, equaling a total of 256. Whenever we saw 128, 128 was equivalent to 0. If I had anything above 128, this would mean that the engine computer is detecting a lean condition, so it's going to be adding fuel for that particular vehicle. If I saw anything below 128, this would mean that the vehicle is running rich and the engine computer is actually taking fuel away to correct for a rich running condition. In our new days, integrator has become short-term fuel trim, or STFT. If the oxygen sensor sends data to the PCM indicating that there's a decrease in oxygen sensor voltage, an increase in short-term fuel trim will occur. Why? Because the engine computer is trying to fix that decrease or lean condition within that O2 sensor voltage. If the oxygen sensor data to the PCM indicates an increase in oxygen sensor voltage, meaning that it's running rich, a decrease in short-term fuel trim will occur. That makes sense. If the computer senses a rich running condition, why would it want to add more fuel? It's going to reduce that fuel, which is why we get a decrease in short-term fuel trim. So remember, a decrease in oxygen sensor voltage equals an increase in short-term fuel trim. And an increase in oxygen sensor voltage equals a decrease in short-term fuel trim. Really good way to remember it. So this way, when you're looking at the data, you can understand that what's happening at that given moment. Integrator and short-term fuel trim are both volatile information. The moment you turn the car off, in most instances, short-term fuel trim goes back to zero. Once you start the car back up, short-term fuel trim is going to start adapting to changes within the automobile at that given moment. So always remember that short-term, in most cases, gets deleted or cleared when you turn the vehicle off. Once you start it back up, short-term fuel trim will then start adapting to changes in the air-fuel mixture through the exhaust or the oxygen content in the exhaust, and the PCM is going to be adapting for those changes. Block learn sounds like the Terminator. Block learn has now become long-term fuel trim, or LTFT. Just like we were mentioning with integrator, block learn was 128 equals 0. Anything above 128 was meaning that the vehicle was running lean, so the engine computer was adding fuel. If you were below 128, this would mean the vehicle was running rich and the engine computer is subtracting or taking away fuel from that particular vehicle. Always remember that block learn and LTFT is a learned strategy. This means that block learn or long-term fuel trim happens over a longer period of time. Over time, long-term fuel trim is going to adapt in order for it to get short-term fuel trim as close as possible to zero. Long-term fuel trim is a learned value, which means that the PCM calculates it based off of previous driving conditions and continuously updates it as it learns the engine's behaviors. In most cases, vehicles now have an adaptive strategy, which means they adapt and learn how you drive. So depending on how you drive the vehicle, whether you drive it aggressively or not, the LTFT is going to be adapting to that, and it's going to learn your driving patterns. Then it's going to be making adjustments as you drive based off of the learned information that the long-term fuel trim has learned based off of your driving patterns. So here's a quick video, so this way you guys can see. The next thing I'm going to do is I'm going to share a quick video with you guys on a vehicle that had a vacuum leak. What I want you to do is pay attention to my short-term fuel trim, long-term fuel trim, and my engine RPM. As you can see at idle, because we're at 867 RPM, my long-term fuel trim is 4.7%, and my short-term fuel trim is at 20%. So at this moment, the engine computer is already detecting that it has a vacuum leak or that it has excessive lean condition, but my long-term fuel trim has not adapted to this situation just yet. So let's go ahead and watch what the data does. So we're still at 900 RPM. We're still 4, now we're at 5, but notice how this one went up to 5 when short-term fuel trim dropped off to 0. Right now we're at about 2100 RPM, and the engine computer right now is still monitoring short-term fuel trim and long-term fuel trim. Notice how when my long-term fuel trim went to 15, we had a small dropout here on my short-term fuel trim. Now, as my long-term fuel trim increases and caps out at about 23%, notice how short-term dropped to 0, but now the engine computer is trying to manage it by adding and subtracting fuel, but my long-term fuel trim stays the same. So again, we were at 2629 RPM. So the engine right now, the reason why we're getting such lean and then rich condition is the engine computer is trying to adapt for that excess oxygen that's in the exhaust stream. However, the long-term fuel trim has maxed out the ability to make any sort of adjustment. So at this point, this vehicle shortly would be setting a code for a 171 for a lean condition bank 1. If you guys are working on a Nissan, remember that Nissan uses alpha fuel trim. 100 alpha is equal to 0% fuel trim control. If you see a Nissan with alpha 110, this means that it's adding 10% fuel. If you see a Nissan with alpha 90 fuel trim, that means it's taking away 10% fuel. So just remember with alpha, it's 100 is equivalent to 0. So let's look at a quick example. Green is short-term fuel trim, red is long-term fuel trim. When you start the car up, your short-term fuel trim wanders off to minus 5%. nothing too shabby. The vehicle should still be in control because it's only 5%. Typically, a good rule of thumb is plus or minus 20%. Now, does every manufacturer have a different variation? Yes. However, over time, you're going to begin to see specifically what most manufacturers are doing with their fuel trim control. So now that we know that our short-term fuel trim has moved over to minus 5%, this is indicating to me that the engine computer is reducing 5% fuel. Could it be a rich running condition? Possibly. It could be the vehicle's cold. There could be a lot of different factors that are causing the computer to take away 5% fuel. 5% is not really an issue as of yet, or dependent on the manufacturer, it might be. But let's keep taking a look here. After my short-term fuel trim has gotten to 5% or minus 5%, long-term is going to then start moving or tracking over to the negative 5%. Once my long-term fuel trim has reached the negative 5%, you can theoretically say that 5% now becomes the new zero. And the reason why this is done is so short-term fuel trim And this is done so then short-term fuel trim can move as close as possible back to zero. So the long-term fuel trim is going to make that long-term adjustment, and then where its new position would be, that would be theoretically relative to zero. And then now short-term fuel trim is going to move to zero. Once short-term fuel trim is at negative 5% for quite a while, what's going to happen is long-term fuel trim is now going to shift over to that 5% mark. This way, short-term fuel trim can now return back to zero and begin to do its normal job. If the fuel control issue persists over a longer period of time, short-term fuel trim is then going to wander back off of zero, and that is going to be added to the long-term fuel trim. So long-term fuel trim is going to take most of the brunt force by moving or making most of the adjustments so we can get short-term as close as possible back to zero. Now, if a car comes into the shop, when you start it up, you notice that your short-term fuel trim moves over to about plus 10%. Again, normally the rule of thumb is plus or minus 20%. However, if we're a little bit over plus 10%, this could indicate the vehicle is running a little bit on the lean side. Because this is short-term fuel trim, again, the engine computer is going to monitor that. And if it begins to notice that short-term fuel trim is staying very close to that plus 10% mark, then it's going to start moving the long-term fuel trim over to plus 10. Once long-term fuel trim has reached the plus 10 mark, this usually starts bringing your short-term fuel trim back to zero. And the reason, again, it does this is because now long-term fuel trim is carrying all that extra load or that extra weight of adjustment, so short-term fuel trim can get closer back to zero and keep doing its constant changes of lean to rich to keep the vehicle in proper fuel control and emission output. Now, what would happen if you're testing a vehicle and long-term and short-term both fuel trim are both at plus 10%? Then you do something out of this world. What do? You raise the RPM. If you bring the RPM up to 2,500 to 3,000 RPM, and you notice that your short-term fuel trim begins to drop off under 5%, what does that indicate to you? That would mean you got a vacuum leak. And how can we say that so confidently? Very simple. What's happening is as the vehicle is operating at higher engine speeds, this extra unmetered air doesn't really have a chance to affect anything because everything is happening so fast. Because of that, as the engine is operating at such a high RPM, that unmetered air is now becoming less evident in the exhaust stream. This is why your short-term fuel trim then begins to return closer back to zero. When you see this anomaly happen, this is a good indication that more than likely this vehicle either has a vacuum leak or an exhaust leak that's being masked by high RPM. Now, to show this to you guys in live scenario, this is the same vehicle that I was showing you guys a little bit earlier with the actual vacuum leak. Now, let's go ahead and play it so this way you guys could take a look. Right now, my engine RPM is at 2,600. I'm going to raise the RPM slightly to about 3,200 RPM. Notice what's going to happen to my short-term fuel trim. As I raise the RPM to about close to 3,000 RPM, my short-term fuel trim now goes from 14, about 4%. My long-term stays about the same because this is, again, a long-term or over time adjustment. But if I keep the vehicle between 31 and 3,200 RPM, my short-term fuel trim is staying between 3 and 6%. So again, this would indicate to me that this vehicle does have a vacuum leak, which it actually does because I induced it. I created a vacuum leak on this car just to be able to show you guys what's going to end up happening if a vehicle does suffer from a vacuum leak, and how simple it is for you to test it in a generic fashion by simply raising the RPM. Now, I'm not saying to just do this test and then call it quits. I'm telling you that this is a good general way for you to verify this vehicle might have a vacuum leak. Then you need to follow it up with some sort of smoke test. Then you need to follow it up with a smoke test, use propane, some sort of way for you to determine where is the actual leak and what is my needed process to repair this particular vehicle. And with that, guys, we've come to an end. I really appreciate you guys hanging around here. I hope this information was very useful for you guys, as it was to me when I learned this from my mentor, Don Wilson. This information is what you need to know to be able to fix any drivability car that comes into the shop. If you have possession of a 5-gas analyzer, even better. That 5-gas is going to help you put these pieces together and come up with a solution to be able to fix that particular car. If this information was useful to you guys, which I bet it was, go ahead and do me a favor, give us a like and a follow. And if you would like to learn more about other systems, drop it in the comments so this way I know what I can do to help you guys out. If you didn't like it, which some of you guys might not, do me a huge favor, drop it in the comments also. If it's something I can fix, I'll probably work on it. If it's something completely out of this world and you're a keyboard warrior, there's nothing I could do for you. Good luck on the next one. So again, guys, I really appreciate you guys being on here. You guys are freaking awesome. Always helping us better the automotive industry, one technician at a time. This always starts with you. And as always, I'm a strong believer in And as always, I'm a firm believer in an investment in education pays the best interest. This is Oscar Gomez from Master Automotive Training, and I'll see you guys on the next one.